Hello student, welcome to all of you. Next physics lecture. This is the video number 26. Myself Rajesh Lagad, physics teacher. Now we are to sing the chapter number 3, kinetic theory of gases and the radiation. The next point we have to see here the Mayer's relation between the Cp and Cv. We know that in 11th standard we can see the specific heat of gas. What is the principle of specific heat? Then we have to define the two specific heat that are the at constant pressure and constant volume. First we have to define here these two specific heat at constant pressure, that is the Cp, and the specific heat at constant volume, that is the Cv. What is the definition of this specific heat at constant pressure and volume? First we have to define the Cp, the quantity of heat required to rise the temperature of unit mass of the gas through the 1 degree Celsius or 1 degree Kelvin by keeping the constant pressure is called as the Cp. And instead of constant pressure we have to say the constant volume, then this is nothing but the Cv, that is the quantity of heat required to rise the temperature of unit mass of gas through the 1 degree Celsius or 1 degree Kelvin by keeping the constant volume, then this is nothing but the specific heat at constant volume, that is the Cv. Then we have to see here what is the relation between these two specific heat, that is the Cp and Cv. Instead of specific heat, if you have to say here the molar specific heat, then we changes the word. Instead of unit mass of gas we have to say here the 1 mole of the gas, then this is nothing but the molar specific heat at constant pressure and the molar specific heat at constant volume, and this is the relation between them is nothing but the Mayer's relation. We have to see here the Mayer's relation. Now consider the 1 mole of gas which are enclosed in a cylinder by the frictionless airtight piston. We have to consider the 1 mole of gas and which are enclosed in a cylinder by the frictionless airtight piston, having a pressure, volume and temperature respectively of the gas. Here let P, V and T be the pressure, volume and temperature respectively of the gas. We have to find the relation between the Cp and Cv. Therefore, if the gas is the heated so that its temperature increases, and this amount of increasing that temperature, which is nothing but the dT, but at that time its volume should be remains constant. If the gas is heated, its temperature increases by the amount dT. At that time its volume is remains constant. Then this amount of heat, that is the dq1, we have to say here, this amount of heat supplied to the gas which can be utilized for the internal energy of the gas, and that is nothing but the dE, and this amount of heat which is denoted by here the letter dq1. dq1 is nothing but the amount of heat which can be supplied to the gas and which is used to increase the internal energy of the gas, that is the dE. That means we have to use here to increase the internal energy. For that purpose we have to say here that is nothing but what? dE, and since its volume is the constant and there is no work done. Okay, and therefore we can write mathematically this dq1 is equal to d, that is nothing but the internal energy, increase the internal energy, and this amount of heat which is at constant volume, therefore we can write the Cv into dt. Its temperature should be increases and volume should be remains constant. Therefore this dq1 is nothing but d, that is the increase in internal energy, which is equivalent to the Cv into dt, and that is the equation number 1. Where Cv is the molar specific heat at the constant volume. Cv constant should be remains constant. On the other hand, suppose this gas is heated at the same temperature. On the other hand, if the gas is heated at the same temperature, but at that time instead of volume its pressure should be constant. We have to take here constant pressure. Then its volume is increases, and this amount is nothing but dV. If you have to understand, on the other hand, if the gas is heated at the same temperature, but the pressure should be constant, and therefore its volume should be increases by an amount dV. And then this amount of heat is supplied, that is nothing but the dQ2. When the volume is remains constant, temperature should be increases, and this amount of heat supplied is equivalent to dQ1, which is utilized for to increase the internal energy. But we have to say here, on the other hand, if the gas is heated at the same temperature, but the pressure is remains constant, so that its volume is increased by the dV, and this amount of heat supplied by the gas, which is used to increase the internal energy of the gas as well as to do the some external work done, and this external work done is nothing but dW. Okay, therefore let dq, this is the amount of heat which is used to increase the internal energy as well as to do the external work done, that is equivalent to dw. Therefore we have to write here this amount of heat which can be utilized for the two purposes, that is to increase the internal energy as well as to do the external work done. Therefore we can write here dq2 is equal to dE plus dW. We can write here dq2. We have to substituting these values about this dq2, dE and dW. dq2, that is nothing but the what? Pressure should be remains constant. Therefore this is nothing but the Cp into dt. D, this is nothing but the internal energy, and this internal energy which is equivalent to dq1, and that is equal to Cv dt. Therefore D is equal to Cv dt. And dW, this is the external work done, and this external work done is nothing but that is the pressure into change its volume, and therefore dW, instead of dW we can write here P into dV. Okay, substituting all these value in this equation 2, we get, see here, instead of dq2 Cp dt, instead of D Cv dt, and instead of dW P dV, we have to substitute here. Then this Cv dt can take this side, then Cp minus Cv, common factor is dt, Cp minus Cv into dt is equal to only P dV. Then according to the ideal gas equation, we know that the PV is equal to RT and PdV is equal to RdT. We know that this ideal gas equation, that is nothing but what? PV is equal to RT. But instead of V, we have to write here PdV. Therefore PdV is equal to R into dt. Substituting this PdV, we can use this RdT according to the ideal gas equation. Cp minus Cv into dt is equal to RdT. dt should be cancelled, and remaining third Cp minus Cv is equal to R. This is the equation number 3, and this equation is known as the Mayer's relation between the Cp and Cv, that is the specific heat at constant pressure and the specific heat at constant volume. The relation between them known as a Mayer's relation, that is Cp minus Cv is equal to R. Instead of this Cp and Cv, if you have to take the molar specific heat mCp and mCv, then where this molar specific heat, we can write this mCp minus mCv is equal to R upon J, or Cp minus Cv is equal to R upon mJ, where J is the mechanical equivalent of heat, and we can also use this formula instead of this Cp minus Cv is equal to R. Okay, this is the Mayer's relations, very important. We have to stop here. Okay, thank you.